Drasma here, and so for today, me and my groupmates shall be discussing about high-order derivatives. So, high-order derivatives. We have learned from the previous sections that the derivative, which is sometimes referred to as the first derivative, is also a function. Thus, it follows that we can also obtain its derivative, which we call the derivative of the derivative, or simply the second derivative. Now the second derivative, being a function, gives us an opportunity to also get its derivative, which is called the third derivative, and the process can be continued successively up to the point that a problem requires. However, note that usually only the second derivative will be required, as it has some of the commonly ascribed properties of functions, such as it can be interpreted as the instantaneous acceleration of an object with a defined equation of motion. Before proceeding, it is a must that you must be familiar with the notations that will be used in this section. In these earlier sections, you have seen the following notations for the derivative of a function defined by the equation y equals f of x. First being the Leibniz notation, followed by the functional notation, third the differential notation, then last the prime notation. As you read other advanced mathematical references, you will encounter other ways of denoting an derivative. However, for the sake of brevity, we shall dwell only in using the four aforementioned notations. Furthermore, you should be aware at this point that the Leibniz and differential notations make use of these operators. In principle, these operators can be attached on both sides of an equation, signifying that we have to take the derivative of each side of the given equation. Now, when we are asked to find further derivatives of a function, it means that we are to take higher order derivatives. So for example, suppose we're asked to find the fourth derivative of the function defined by y f of x, then we must first get its first derivative, then its second derivative, and its third derivative. The fourth derivative of the given function can be denoted by any of the following. Thus, generally, in the following, the nth derivative of a function of y equals f of x can be denoted by this. So let's have an example to start us off. Consider the polynomial function given by y equals p of x is equals to 5x power of 6 plus 4x power of 5 minus 5x squared and minus 80. Let us try to get the general formula for the nth derivative of p. So here's the solution. And now we just multiply 6 to 5, 5 to 4, 2 to 5, and cancel 80. And now we have our first derivative, which is now 30x power of 5 plus 20x to the power of 4 minus 10x. And now we just continue doing this until our value of the highest derivative will become 0. Now we can see that from the seventh derivative, our highest value derivative is now 0. so we can stop there. And here is our final answers box. So let's have an example to start us off. Consider the polynomial function given by y equals p of x is equals to 5x power of 6 plus 4x power of 5 minus 5x squared and minus 80. Let us try to get the general formula for the nth derivative of p. So here's the solution. And now we just multiply 6 to 5, 5 to 4, 2 to 5, and cancel 80. And now we have our first derivative, which is now 30x power of 5 plus 20x to the power of 4 minus 10x. And now we just continue doing this until our value of the highest derivative will become 0. Now we can see that from the 7th derivative, our highest value derivative is now 0, so we can stop there. And here is our final answers box.
Crisabel Shane Gaviana from 11th MF Adroit class, and I am going to give some examples of higher order derivative.
Example. We have f of x is equal to x cubed minus 12x squared plus 4x plus 2. So to get our first derivative, we need to get the derivative of each term. So we have y prime is equal to the derivative of x cubed, which is 3x squared, minus the derivative of 12x squared, which is negative 24x, and the derivative of 4x, which is 4. So since 2 is constant, it will automatically become 0. So this is our first derivative. To get the second derivative, we need to get the derivative of each term in our first derivative. So we have the derivative of 3x squared, which is 6x, minus the derivative of 24x, which is negative 24. Since 4 is a constant, it will automatically become 0. And lastly, to get the third prime, we need to get the derivative of each term in our second derivative. So the derivative of 6x, which is 6, and since negative 24 is a constant, it will automatically become 0. So next, let's proceed to our second example. So we have f of x is equal to the square root of x plus 3. Since it is a radical, first we need to rewrite this into exponential form. So we have f of x is equal to open parenthesis x plus 3 close parenthesis to the power of 1/2. So let's apply here the chain rule. So we will going to multiply 1/2 to the other side. So we have y prime is equal to 1/2 times x plus 3 to the power of 1/2. And then we will subtract 1 to our exponent. Now let's simplify. Y prime is equal to 1/2 times x plus 3 to the power of 1/2 minus 1, which is negative 1/2, times the derivative of x plus 3. So since the derivative of x is 1 and the 3 is constant, 3 will be automatically become 0.
So our first derivative is equal to 1/2 times x plus 3 to the power of negative 1/2.
Next, let's get the second derivative. So since our first derivative is y prime is equal to 1/2 times x plus 3 to the power of negative 1/2, let's multiply our exponent negative 1/2 to the other side. So we have second prime is equal to 1/2 times negative 1/2 times x plus 3 to the power of negative 1/2. And then let's subtract again 1 to our exponent.
So we will have 1/2 times negative 1/2 is equal to negative 1/4 times x plus 3 to the power of negative 1/2 minus 1. Now let's simplify. So we have second prime is equal to negative 1/4 times x plus 3 to the power of negative 1/2 minus 1 is equal to negative 3/2. So since the exponent is negative, let's get its reciprocal. So we have second prime is equal to negative 1/4 times x plus 3 to the power of 3/2. So this could be our final answer, or we can change it into a radical. So we have second prime is equal to 1/4 square root of x plus 3 to the power of 3.
Good morning, everyone. I am Jarens Bedando. Higher order derivatives. We have two examples. The first one, the given is f of x is equals to 8x raised to the power 4 plus 1/3 x cubed plus 9x minus 5. Step 1 is to differentiate. To differentiate, you have to multiply the exponent to the numerical coefficient. Then subtract 1 from the exponent. So we have the first derivative (32 x cubed plus 2/3 x plus 9. You have to disregard the x minus 5. Then, repeat the process to get the second derivative. To show the number of derivative, you have to put f, then one line for the first derivative, then x, and copy. For the second derivative, you have to put two lines, then same process. 3 times 32 is 96, then subtract 1, so you have 96 x squared plus 3. You have to disregard the x plus 9 to get the second derivative. The second example is f of x is equals to sine 5x. First thing you have to do is change sine to cosine and copy 5x. because according to the differentiation rule, sign should be changed to cosine. Then multiply 5 by itself, so you have 25, and applying the differentiation rule, which is negative cosine, so the answer would be negative 25 cosine 5x. This will be the first derivative. For the second derivative, just repeat the process. Negative 25 times 5 is equals to 125. Change cosine to sine, so you have negative 125 sine, then copy 5x.